Hey, welcome back. So, this time we're going to look at something new. Last time we looked at tables and we learned a few new opcodes: LDX, STX, LDY, STY. So those are, as I've mentioned before, those are called opcodes, those 3-letter commands. So we're going to look at more opcodes today, but before we do that, let's look a little closer on the assembler. So you remember that I said that it's a good idea to call the programming language assembly, and the actual assembler, we'll call that assembler. So what is the assembler? Well, let's take a look. So first of all, there are many different assemblers. Some of them run directly on the Commodore 64, and some, in our case, run on a modern PC. If you run it on a modern PC or another computer than a Commodore 64, then it's called a cross-assembler. But anyway, there are many different assemblers, but the assembler that we're using is called Kick Assembler, and that's a cross-assembler since we're running it on a modern-day PC. Or a PC other than a Commodore 64. So there are many different ones. Now this can create a problem for you if you go online searching for Commodore 64 assembly code and you find something, but it's written a little differently than what you're used to. Then that might be because the person who wrote that was writing that code for a different assembler, and you can't directly copy it from, assemblers aren't 100% compatible in that sense. So you would have to modify the code in some places to make it work for Kick Assembler, for example. So it's just something to be aware of. And as I said, it's a source of confusion, especially in the beginning. But the one that we're going to use, the assembler we're going to use, is called Kick Assembler. So now you might be wondering, what exactly does the assembler do? Well, let's imagine over here that we have written some code in Sublime, our code editor. So we have written some assembly code here in Sublime, and now I want to run this. We have already done this a few times, but let's say that I want to do that now. Well, then I press F7. Because we have a setup where I have Sublime and Kick Assembler connected, and then we have connected the Vice Commodore 64 emulator into that. So we have a pretty nice setup where everything is connected. So when I press F7, all of that happens automatically. So when I press F7 now, the Kick Assembler starts up and goes through my code. And what it does, it translates my assembly code into something called machine code. Now I have displayed it here in binary, but machine code, that's almost the same as assembly code, but there are no commands there like STA, LDA. In machine code, there are only hexadecimal numbers, which at the end of the day are turned into this, ones and zeros, because that's the only thing the computer can understand. Any computer. The computers can only understand ones and zeros. So basically what the assembler does, it takes our assembly code and makes a binary file for us. So let's take a little look at that now. So here on my desktop I have a folder called test that I just created. So in my folder test, that's empty right now. So I'm going to create a new assembly file to put in here. So like you remember from before, we need to start by writing basic upstart 2 with a main in parentheses. Now this word main, this could be anything. It doesn't have to be main, But the important part is that you have to have a corresponding version of that name down here. Because basically what this is the start of the program. So if you write test here, the word test also needs to be down here. But I just like to use the word main because it's a very descriptive name. Alright, so basic upstart to main and main. So if I just make a very tiny little piece of code here, I could write inc d020. Do you remember that? Well, let's take a look. And then I'm going to jmp main. And I'm going to save this file. And I'm going to save it in my test folder. Now it's important that we name this file. You can name it whatever. I'm going to name my main file main. But anyway, the important part is that we say .asm at the end of the file. So we need to specify .asm as a file type for our file. So main.asm, that's my file. Okay, I'm going to save that. And you know what? Let me show you something first. So now I click cancel. I didn't save the file. So now you can see that all the text here is just white. But when I save my file now as main.asm and save, now you can see that we got some color codes here, which is really nice because the opcodes are now purple and any memory address like this turns yellow. So that's a really nice function here in Sublime. So, but anyway, now I've written a small program which I'm sure you remember increases the border color. Ink that increases whatever is in a memory address. What memory address are we talking about? D020, that's the memory address for the border color. After that, we have jmp jump. So that tells the code to jump to whatever label we specify here, which is main. So we just jump up here and we run this all over again. So an infinite loop. It's going to go over and over and over again. So what happens now? Well, first of all, let's take a look at my folder. Here's my test folder. Here's my main.asm file I just created. Alright, fine. Now, let me just press F7 to run this. Remember, now Kick Assembler starts and it's going to transfer or translate my code here, my assembly code, into machine code or binary. So, let me do that now. I'm going to press F7. And there we go. So the code was assembled. Everything went just fine. No error messages. And here we are. The device Commodore emulator started and it automatically loaded the file that I just made. So it's a really nice setup. Really handy. And obviously we can see that my code is working. But let me quit that for now. Let me go back to the folder, test folder. So now you can see that we have certainly got a new folder here. Before I just had my main file in here, but now I have this new bin folder as well. So if we go into the bin folder, we can see main.prg. So it's called main because my file here is called main. So main.prg, that file is what the emulator runs. So I can actually double click this one now. And that starts up my program that I just made. So this file, it's kind of cool actually, because this file is a file that you can run on a real Commodore 64. But you need some sort of device where you can transfer files from your computer onto the Commodore 64. But this is the binary file. So what we can do right now, this, as I said, this is a binary file. So we can't open this in Microsoft Word, Notepad, anything like that, because it doesn't look like this anymore. But what we can do, we can open it in a hex, some software that can read binary files. And I happen to have one on my computer, so I'm going to open my PRG file in I have a Mac here, so I have an application called HexFind that can open binary files. So I'm going to open that, and this is what the assembler turned my code into. This thing right here. So it's only numbers, and this is machine code. Now it's represented here in hexadecimal, so you can see some E, 4C, stuff like that. But as I said, at the end of the day, it's all just binary numbers. Alright, well, what do we have in here? Well, let's look at the first 2 bytes here. It says 0108. If we read those backwards, 0801. That might be familiar to you, because we have talked about that before. 0801, the very start of the free basic area. So you remember this, right? 0801. So the first 2 bytes of the file specify where in memory this is going to start. So if we look at all these things together, we have our code here, we have our excuse me, my binary file here that the assembler created, my main PRG file, and I have my memory map, or my Excel file here. So the green area, that's the free space in Commodore 64 memory. So my code starts down here, 0800. That's where we start. So the first 2 bytes here are not actually put into the memory of the Commodore 64. But from here, these bytes over here, that's what we talked about last time. The basic, the line of basic that actually starts our program. So this thing, 10 sys 2064, that's this thing here. But after that, here, this is my actual code right here. So it's just numbers like this. And we're going to take a look at why these are the numbers that they are. But if we look at this, D020, that's this memory address. And 080E, that's actually the start here. Let's not go too deep into this because we can quickly get confused here. But the point is that this is what's put into the Commodore 64 memory down here. So starting at address 0801, we start putting the lines of the basic code. And then we continue on with this assembly code. So we already, just with this tiny little code, we'll already start putting some bytes into the memory right here. So there's one more thing I want to show you. So let me just close my Excel here, and let's close this one as well. So if we go back to my folder now, my test folder, so if I go into bin now, we have looked at the main PRG file. So there are several files here, but this one is interesting for us, but this one is also interesting for us. The main_build_log.txt. What's that? Well, let's open it and take a look. So this file is created by Kick Assembler for us. So it's just almost like a log file of how our code is set up. But what's interesting about this is that later this file is going to become really useful for us, because we can copy the contents here. Copy the contents of the main build log file. So I'm going to copy that, and if I go to a special web page called Noice Kick Assembler Memory Viewer, and I just paste my code, I paste this from the main build log file. If I paste that in here, then we can see over here where our memory is starting to fill up. Now right now it's so small that we can barely see a little line down here. But if you remember from the Excel file I just showed you, this is 0800, so that's where we're starting to fill memory. So if I had thousands of bytes, we would see this grow up here. And when you're making a game, a big game with a lot of graphics and a lot of data, this is really handy because you can see how much space you're using and what space is free and so on. So this is a really useful tool for us. We're going to come back to this one. But the important part here is that the assembler does all of this for us. So just by writing a little piece of code, pressing F7, we get not only the binary file here, but we also get this file, and because of our setup, we also launch the emulator and automatically run this as well. Alright, well, let's quickly take a look at more opcodes before we end today's episode. So, until now we have looked at just a few: LDA, STA, LDX, STX, LDY, STY, and we have also seen INC and JMP. But if we go to another website here, 6502.org, tutorials and aids. So here are the opcodes that we can use when we're writing assembly language for the Commodore 64. So there are 48 or something. I think it's 48 here. 48 opcodes that we can use. And as I said, LDA, we already looked at that. STA, same with LDX and STX and so on. So these are the ones that we can use. Before I show you anything else, let me just click LDA now. So this is a description of the LDA command, the LDA opcode, load accumulator. So you remember from our machine code file that we could see that everything was just numbers. Well, that's because every little opcode has its own hexadecimal number like this. So if we open up our main PRG file again in hexfind, and we just quickly take a look at this D020 thing. So we have an EE in front of, and by the way, don't worry about the fact that those are backwards right now. As I said, 0801, we are reading them a little backwards right now. D020. don't worry about that right now. We're going to come back to that. But EE, what's that? Well, let me try to search for EE here. And as we can see down here, the hexadecimal number EE, that's actually a hex code for the opcode INC, which makes perfect sense for us because that's what I used over here, INC. So in my machine code file, EE D020, that's exactly what I wrote over here, INC D020. So it just looks a little weird maybe here in machine code. Now we're not going to spend too much time on this because machine code can be a little hard to read and a little confusing, but I think it's important that we at least know about this. So we have looked at LDA, STA, as I said, and a few more with the X and Y register. What we haven't looked at is how we can add and subtract numbers, but we are going to look at that really soon. So add, for example, that's ADC, add with carry. We have also something called SEC. Oh, whoops, what happened here now? SEC, that's subtract with carry. I don't know what was up with that link, but whatever. So anyway, here is the list of the opcodes that we can use, and we are going to use quite a few of them. Especially, let's see if we can find it there, JSR, jump to subroutine, and also something that we have seen before, RTS. That's the one that I used to exit my code. Return from subroutine. But I think this is enough for now. Now, I said that we were going to look at opcodes, and to be honest, I had planned a little more to spend a little more time with opcodes here, but I think this is enough for this episode. Knowing how the assembler works and what actually goes into our code, how this actually works, how it's set up, it's really important because we need to understand how the memory works and what's actually put into memory. So for example, writing INC here, that actually takes up, let's see, INC, let's go back to that one. So we can see that INC, the EE, it says here len, that's length. That actually means this opcode takes up 3 bytes of memory. So just by using this, you take up 3 bytes of memory. And that's something that we need to keep in mind, because for every single opcode that we use, we are actually filling up our memory. So we're not just filling the memory with graphics and music and things like that, but the code also takes up space. So that's important to remember. And if you ever wonder how many bytes a certain opcode takes, then you can just go to this web page and look at it and see that this takes up 3 or 2 bytes. Most opcodes take around 2 or 3 bytes. But if we ever need to know specifically, we can go to this web page. Okay, well, I think that's enough for today. So let this sink in, and I'll see you next time. Bye bye.